high bench is another. And they have some analytics, a lot of them are of course based on TPC and that type of data systems, but some of them have things like, they use Hadoop and Spark and things, and have other types of applications, but they don't do streaming. So we suggest we need to have a benchmark set. As far as I know, no NSF facility supports streaming data in a simple fashion. Astronomy data, which is streaming, is analyzed, for instance, at Berkeley and NCS, or Berkeley's DOE, but NCSA is NSF. But these are not analyzed on a software environment where if you have your own streaming data, you can reuse it. So there is no service called analyze streaming data, whereas the clouds have that. Google, Microsoft, and Amazon have operational streaming services, and I pointed out the only weakness is it's not quite obvious that they will do scientific, or we're mainly focused on scientific research, but it's not clear they do non-commercial workloads. They might do. They're nicely done, but it's not clear. All right. Let me just turn to NIST. So, actually, these workshops came out of the work I did with NIST. And NIST set up a few years ago, 2013, a Big Data Public Working Group. And I think that working group, which actually is, I will miss that telecon at 1 o'clock this afternoon because of this meeting. And they meet actually, they have telecons every week. And they have some pretty interesting subgroups. One is the one I was in charge of, which is now actually got NASA involved. Piyush Malhotra from NASA Ames is the new co-lead with me. That's on use cases. And that study of use cases highlighted to me the importance of streaming. The other ones, well, there's definitions, there is an architecture, and there's a very good security and privacy working group. So, and these are all published. The results of this activity, which started in July, I think it started at the end of June 2013, is fully published in a set of 6 NIST reports, of which I've only given you one of them now, which is the use case report. But if you change the -3 at the end, you will find the other reports. So there is an architecture. I don't really want to talk about it, but if you're thinking about the geospatial architecture, it might be useful to note that NIST has thought about the general big data architecture. And they're doing it partly because NIST obviously has a great interest in standards, and actually this work is part of an effort with ISO to set big data standards, which again I think should be relevant to you. Well, actually, this just points out that we did consider streaming in this, so we have a whole set of sort of generic diagrams. This is the architecture, which is the Apache Storm architecture. It has Storm, Kafka, HPC, Zookeeper, and this is how streaming data is buffered. In Kafka, although Kafka doesn't work, well, you should use RabbitMQ instead. You pick out some events and then you run them through analytics, which is done through Storm. And Zookeeper coordinates all of this. And here is a simpler Spark, Hadoop, Giraffe type architecture where you just have data that's probably stored. It's stored and is accessed from HDFS or something. You run your favorite analytics, and then you put your favorite library on top of that, and you do some data analytics. And then this is just a minor refinement of that, which notes that a lot of scientific data is taken in batches. So you have all that. So what I did was, actually I should have put the slide in which had all the applications. Anyway, there are 51 use cases. Of those 51 use cases, this must have it. 16 of them involve GIS. So there is, and so there's a lot of earth and science and further science and things like that. And, So anyway, I looked at how, if you look at the features of these things, 26 of them are what I call pleasingly parallel. This is out of 51. And that's actually pretty relevant. A lot of people tell you they're doing machine learning, and you ask what they're doing is they're running machine learning on an individual core or node, because actually each event is being processed in the middle. That's not negative. That's actually, if that works, that's wonderful. But it has important architectural considerations, because you can run pleasingly parallel on the cloud. If it's not pleasingly parallel, you will not run well on the cloud, because the communication overhead is too great for it. Well, you can run on the HPC clusters at Amazon, but traditional OpenStack systems will not run well. So actually, I'm just saying about another, actually, 23 of them were what I call iterative MapReduce, which is MPI or Spark or Flink running iteratively. 9 of them, there's obviously a lot of work in graph algorithms, and 9 of them involve graph algorithms, and so on. But this is why I organized some streaming workshops. 41 of those 51 were streaming. Now, they weren't necessarily drastically streaming, because I say the Large Hadron Collider is actually streaming. The accelerator is producing one event at a time. But actually, it's batched when you process it. You write it, you trigger on it, you run that streaming data through a trigger, write the events you're interested in to disk, and then you distribute that disk in batches. But actually, the Atlas collaboration is interested in moving that to a pure streaming solution, because this batch solution has lots of data copies involved, and they do not like it. It seems to be very inefficient. So there's some interesting issues there. So I want to, given the small amount of time, I must be near my 5 minutes.
We're getting close to that.
Yeah, I reintroduced something as a result of that NIST work called the OGRES. And they're called OGRES because National Research Council had big data giants, and Berkeley had parallel computing dwarfs. And so we decided to have big data OGRES. And so they are a consistent, they are a set of 50 features, of which, say, well, the ones I've already mentioned, pleasingly parallel, using on the data, number 10 is geographical information system. So using GIS as a feature, being pleasingly parallel as a feature, velocity, volume, variety, veracity are features. And they were divided into 4 categories depending on sort of, well, this, try to separate, make similar things go together. The ones here on the top left are actually the type of the analytics which are being run. Like you'll see, search is one feature, classification is another feature, and so on. Right, so we did that, and we will skip over that. I would just mention a project I have, which is funding me to do this, and probably funding me to come here. That's a project called SPIDLE, for Scalable Parallel Interoperable Data Analytics Library. And it is fantastic in this project where you have lots of people. That's necessary in NSF, you have to have lots of people. Lots of different organizations. And it's shown in this picture here. It has 4 components. So it has applications, pathology, proto science, biomolecular simulation, and network science. It has these OGRES came out of that project. MIDAS is our software that ties things together. I will have 1 or 2 slides on HPC-ABDS, and SPIDLE is the library. I should point out that whereas in high-performance or parallel simulations, libraries like LAPAC and ScalarPack and PETSI and things are incredibly successful and very good. The libraries in big data for parallelism are not very good. They are terrible performance. So the purpose of this project is to produce higher performance libraries. And I just added you there, OGC, geospatial use cases. And given I have only a few minutes left, I will at least introduce you. So I should point out, one of the things we're trying to do in my project, this project and other things I'm doing is to satisfy the Strategic Computing Initiative goal of tying together big data and exascale simulations. And we would claim to know how to do that. And there are various obvious reasons why that's a good idea. I mean, as a sort of simple example, if you go to deep learning is always run today on big HPC clusters because it uses GPUs. And that's at the heart of deep learning, at least for images, is matrix multiplication, which we all knew would run very well. That's why the people at Stanford who first did this did that. And if you look at most machine learning, it has actually linear algebra at its core. And so it actually benefits tremendously from HPC systems. That's why it's important to know whether you're doing pleasingly parallel. Because if you're doing pleasingly parallel, that matrix multiplication is running on a node or on a core and doesn't need high performance interconnect. If you're doing it on a parallel system, you have to worry about it. And so, well, HPC-ABDS stands for High Performance Computing Enhanced Apache Big Data Stack. And I'm not going to go through these 350 Apache software systems, but our approach is very simple. The Apache stack, it is not designed for performance. Spark and Hadoop and things have and even Storm, they do not have good performance. They're designed for other things which are very important, like productivity and functionality. So our approach is to take the Apache stack, because it's going to win, because it has more people in it, it has wonderful software communities building that software, and to add HPC to the Apache stack. That's our software approach. And so, let me just see if I can do this. So we actually make Java run fast, it actually runs faster than C. So here is an example, which is our most mature product. It's called HARP, and it's basically a plug-in to Hadoop, which effectively puts scientific interfaces and MPI-style performance runtime into Hadoop. If you look at the Apache stack, there is no Apache project called runtime. They all use ad hoc runtimes. They sometimes use Netty, which is the Java communication library. They sometimes use publish subscribe. They never use high-performance runtime. And their architectures do not work well for high performance. They work wonderfully about what they're designed to do. And then the final is streaming. So we tried to use Storm streaming, which is the Apache streaming system, and we were using it to control robots, and we were trying to run the high-performance applications from Storm. And that's to try to get the application to run in time. We're doing image processing applications from Storm, and Storm works wonderfully. It's a very elegant architecture. I say when you run Storm, you have RabbitMQ or Kafka buffering the data hands events to the analysis program, which is controlled by Storm. But if you look at that, Storm only supports data flow. It does not support parallel computing at all. That's important to know. Motor, Heron, Flink, and Storm only support data flow. Spark is sort of slightly funny, but those other three only support data flow. They do not support parallel. They do not support any of the usual primitives of parallel computing. Anyway, so if you look at that here, so we took Storm, and this is one example. We took standard MPI style broadcast operations and added them to Storm, just plugged them in and removed what Storm had in it, and we got a factor of 4 in performance improvement. And we're doing the same now with Heron, working on Twitter. So, at the end of this, I'm going to summarize, and I try to show you that There's some pretty interesting work from these streaming workshops which have identified, which have done surveys of the world and identified things to do. And I mentioned some of those things that need to be done, from community activities like benchmarks to actual technical activities like deploying a government facility that will actually support streaming with a sort of streaming architecture such as Storm. As far as I know, Storm and Heron are the best streaming architectures. They're very elegant with the buffering and the long-running analysis programs, and my guess is my intuition is that's the right architecture. But there is no NSF facility you can go to and say, please give me 18 nodes running Storm. They will not know what you're talking about. And then I pointed out that the NIST project, which actually identified the importance of streaming, had some useful input for people building big data architectures, and including security, but also the actual architecture and this application analysis. And then I noted that if you're trying to see what